going to tell us about the work where EDF has very large-scale systems being simulated. Large a large energy company, and the way that they took functional programming techniques, particularly Erlang, to do that. So,
hello. We are using Erlang for discrete event simulation, and I would like to share with you the joys and sorrows that we have. So I will start by telling a bit the functional service, which is given by the engine. Then technical architecture will be mentioned. I will be very short in terms of algorithm, but I will try to explain why it is of interest for us to do so. I will try to give some information about our feeling about the use we made of functional programming and the few problems that we observed. And I will mention some future about relationship with Erlang. So, our software is named SimDiscard. It stands for Simulation of Discrete Systems of All Scales. Actually, it's a simulation engine, not a simulator as such, a simulation engine, which is to be used for discrete event simulation, DES, and ours is synchronous. The main specificity of this software is that it is concurrent. By that we mean that it is both parallel and distributed over a set of computing nodes. And we aim at maximum scalability because we have digital systems which are of large scale. So we aim typically to be able to simulate dozens of millions of complex embedded instances in iteration. That's the plan. The engine is generic, domain agnostic. So we could imagine that we could apply it to, for example, ecosystems or vast smart metering systems for the utilities, which is of course the use case that we work on. And over time, we felt that it was a more generic tool than expected, and we saw that some problems that we had for in terms of energy could be seen as complex systems, and we spotted a few examples of that, and we spotted also that in the current state of the art, there are not many tools which are able to be of large scale, because most of them are state control, and they that brings some problems in terms of cooling times, for example. So if you take the engine, you add a bunch of models which are domain specific. At least one simulation case, you get a simulator. So here are the main functional services that we offer. We will try to see how they work together in the course of a simulation. So first task is to give the engine the settings which are of interest for a simulation. It means the simulation settings, whether we are batch or in an interactive mode. What is the fundamental frequency in the engine? By default, it is 50 Hz. We will also to specify deployment settings, at least the list of hosts that we can try to access to in order to share them in terms of computing resources, so that the solution can be distributed over them. And of course, there are settings which are specific to the simulation case. Then we deploy the simulation on the host that were given. The point was that we didn't want to add a prior install in the nodes which take part to the simulation, because we use the HPC clusters and we cannot anticipate on which nodes we will end up. So the engine is able to deploy over a set of computing nodes which just have a suitable Erlang version on them, and then description. We can specify what are the initial sequences, and then we place and create model instances. We call them actor for short-term name. So we have got the load balancers to ensure that we can make an effective use of all the computing nodes. And then comes the bulk of the work of the simulator and the scheduling of the model instances. We have shown here that we have a hierarchical time management system. It is the main role of the engine to ensure that every model instance is appropriately scheduled and that some properties are preserved. We offer as well additional services, the distributed price system to develop the system, some stochastic support because most of our models are given by stochastic variables, so we have to provide built-in density coefficient functions. We also the performance tracker, which allows to monitor the resource consumption, the number of instances of each model which are created over workload time and over simulated time. And we provide specific systems for specific needs in terms of information sharing. If you have a few writers and many readers, then we should better use something like that. So we have different trade-offs that can be used to enhance the performances. We can plug into any model instance probes, which can be either basic or virtual. When they are virtual, we are using the data logger, which is relying on a distributed database. There are two kinds of probes because we have two different needs and we need two different trade-offs. And then for the results of interest, which were specified as solution settings, we can take the time series we collected and generate plots from them, and then we can, once it is done on a distributed way, we can retrieve them for the user in the launching computer. There are also a lot of post-processing which is done, but it is outside of the engine, so I haven't mentioned it yet. What is difficult for this kind of simulation is that we want to enforce a few properties which are interesting for us and which are not preserved by default if we rely on a basic implementation. The first of which is very basic. We just want to ensure that the causality is respected. I have a few slides in analysis to show that in a distributed system it's not by default true, so we have to use an algorithm to ensure it is preserved. Another key point for us is to ensure that we have total reproducibility. We see our engine as a mean of making a decision this is a kind of decision-making tool, and we want to be able to compare two situations in which we change just one parameter, and if we have that total reproducibility, we cannot correlate the change in the outputs to the change in the inputs. So it is a very important property for us. And we need also some form of ergodicity. We call it that way to say that once you are reproducible, you can see always the same sequence of events that happen. But another interest of the simulation is to show all possible trajectories of the system. and the engine reorders these messages so that the properties are respected. So the point is, for the business need we had, we wanted to be able, in the years to come, to be able to tackle simulation with 50 million instances, which is roughly the size of the metering system in the British case we were producing on. And the purpose is that if ever we had as many cores, we would be interested in evaluating all of the model instances in parallel. Of course, we have not that many cores. And also, there are challenges which were not related to scalability, but which were difficult for us to overcome. Business people specify a system in free text often, or with some kinds of block diagrams. We had first to use proper UML, and we had to translate their data flow maps and define some state machines to do so. And when we had finished this task, we had a proper object-oriented view of the target system, but we had somehow to map this OOP view into a functional one, which is orthogonal, I would say. We also had to take care of some stochastic problems we wanted to be able to reduce and to manage. Also, the people who were writing the models were not functional developers, and they were not able to manage concurrency, take care of deadlocks, or so on. We wanted to define a language for them which was as simple as possible, and we wanted to ensure that each model, the behavior of each model was defined sequentially. What is parallel is the parallel evaluation of all models, each model being sequential. So it was to allow for a simpler development process. And we wanted to remain as high level as possible because with other engines, people who write models had to support C++ templates and so on, and it was not the right population to do so. So we wanted to say as much as possible, very simple. So an example of use, the biggest one of our engine is the Clever simulator. It was a British project on which we worked. So at the basis of everything was Erlang, the Erlang virtual machine, on which we added a few common structures that were relevant on our way of programming. And so it was a kind of toolbox for us. We added a hooper, which is a lightweight layer which allows to map object-oriented programming into functional programming. We added a discrete trace system because otherwise we can see what happens in the critical system. Here is the engine as such. So all this layer provided an EPI for an engine, which was used here by a specialization layer for telecom and processing description. I can't mention every aspect of it, but it was developed by the University of Bristol with some help from British Telecom, and its purpose was to have to find a consensus on the end of each decision ticket, which is obtained through the wood time manager. And the goal was that if we wanted to be scalable enough, we had to have most of our distribution services as much as possible distributed. So the time management is distributed, a lot of data exchange is distributed as well. And what we wanted also was to minimize our dependency on latency, because what kills the performances of most synchronous engines are the latency between two clicks. And we managed to minimize it, and we created a large number of messages for lower latency. And most of these messages are made to be purely local. And to obtain that, we have to have a smart placement system which allows to express the constraint that if two actors are very coupled, they should end up in the same node as close as possible, so that they can communicate purely locally instead of going to the network. Even if we have low latency links on the cluster, we prefer, of course, to have co-allocation. So it is true for placement, it is true for scheduling, and we have also systems which have to be also designed for a minimal latency. We mainly use our engine on HPC clusters in Bristol and in France. And we made some tests of a tiny card, but we had not much time to do so. So it is still pending. So, a question that arises often is why we chose to use the functional programming and why Erlang. We came from backgrounds where C++ and Cobol are the norm, and we suffered from that insofar that development is very heavy, very long, and very painful. And having the possibility of writing once a program and having it work on multiple hosts with not much pain was a real benefit for us. Moreover, most of the systems we want to simulate are implicitly concurrent, and we believe that if we use technologies which are concurrent as well, we tend to bridge the semantic gap, and we tend to have solutions that match better our needs. We had a few speculations. We knew that we had to create some words, sequential speed, and memory footprint. But as soon as you are distributed, you can think that you have many nodes and you can overcompensate it. So in HPC, clusters are expensive for most energy utilities, and so that was not a big problem. We wanted to go higher level, as I said previously, and we thought that we could do, if needed, more complex algorithm, which we wouldn't dare to have tackled if we were still using C++ and Cobol. So it was how we see it, and of course the performances matter, but the development effort as well. So we have to find a trade-off, and we thought that Erlang was a better trade-off than what we used previously. And finally, we are not dealing with number crunching here. There is no ingestion of large matrix or so on, so it was not a problem for us. And all these speculations were quite good, and we had a few gains that we were not looking for especially, but we were happy to have them. And a side effect was also that we had to enter a bit the functional programming world, even if it was something new for us. A few issues arise, but globally the outcome is very positive. But as time went by, our partners developed very complex models, and finally we became RAM-bound and CPU-bound, and so some trade-offs had to change, but that's not the fault of them, obviously. We believe we could do a lot better with our resources, but currently we have not measured it, so currently it's not a problem that we want to tackle, even if we are not very optimized. I am fully aware of that. The problem to map object-oriented programming to functional programming was overcome quite easily, but it had to be done because we wanted our model had relied on polyconformism, inheritance, and so on, and we wanted to have that. And finally, of course, there are always problems with distributed computation. We had a few problems with system diagrams which couldn't provide conformism. There was a small race condition that we triggered in the virtual machine, but it was a minor detail. We had to fight against error messages. I was a bit ashamed that we hadn't at that time line numbers in seconds, which is not true in our 15 version of Erlang. And it was always disturbing to see that if we misspell an atom, we can trigger unexpected behavior that we discover only at any time. And of course, we made a bunch of deadlocks and price conditions because it is intrinsic to the problem. program and functional one. What we wanted was multiple inheritance, polymorphism, and state management. It was the most important for us. So how we do that, it's easy. I will show you some code. You define the class, the basic Erlang class with basic Erlang construct. You just define your model classes, direct model classes. You define methods, which can be either request or one ways, or it can be static as well. And you define a constructor, which is called by new operators. You can define a few methods. And once this class is combined, you can use it this way. So for example, you can create an instance of class cat, which is following parameters. Then you have a PID with which you interact to trigger methods and get results. So I would say that it's just plain Erlang code currently, but to do better, we should use metaprogramming so that we are able to generate a kind of test virtual table, a bit like C++ would do. But for that, we would have to use parse transforms.
Does the simulation need to be, does it need non-determinism? Or would it be useful to have a framework where the concurrency is guaranteed to be deterministic?
No. During a time step, the order of execution of model instances does not matter. I don't know if it's the answer to the question. But so we do not want to enforce any particular order into the operations as soon as they happen for the same thing. Okay? Because there is one tendency between a request sent by an instance and the first moment the receiver can process it. So during a time slot, whatever happens, there is no direct relationships between instances. You see? So the scheduling does not matter. So what we do is that inside the time tick, we let the Erlang scheduler process all the instances, and as soon as the consensus is reached upon the end of tick, we are able to jump over the next non-idle tick. So it doesn't matter for us inside tick.
Okay, I think we should stop here because we're about